Green light.
All right, welcome back, everyone. Let's get settled in. So as we begin another new lecture series, I'd like to ask David to introduce our next lecture.
All right, very good. So we are delighted to have as our next lecturer, Sebastian Mizera from Princeton, who's going to tell us about a very exciting topic, the gravitational S matrix.
All right. Well, thank you, David, for this wonderful introduction. And let me thank the organizers, the local and the scientific organizers, for setting up this wonderful summer school. It's actually my first time at TASI and my first time in Colorado, and I'm enjoying it a lot. So I decided to talk about the topic of the gravitational S matrix, which to me is very exciting. And I wanted to share that excitement with all of you. I think the topic is exciting for many reasons. The first reason is kind of apparent from the title. It connects the gravitational physics and the kind of S matrix topics, which are more traditionally associated with particle physics. So this is kind of a marriage of ideas. Another reason why it's exciting is I think that, especially nowadays, it's quite topical. There's been a lot of work on the emergence of classical physics from quantum field theory, especially in the view of the excitement surrounding LIGO and other gravitational wave observatories. So there's been a number of, basically an explosion of activities in trying to understand, quantify the amount of gravitational radiation emitted in the two-body systems. And the final reason why I'm excited about this topic is that I think there's a lot of it's very easy to start asking basic questions and land on those for which the answer is, well, no one knows. And I think that's exciting because there's an opportunity for you. We need a lot of young, motivated people in this area to make progress, especially on the intersection between the S matrix topic and things like quantum information and non-perturbative gravity, which I think has been lacking so far from this topic. Okay, so I have to start somewhere. So I'm going to start from motivation. There's many ways to motivate this topic, especially that it's so the body of literature is so ginormous. I'm just going to take a specific problem, specific kind of Gedanken experiment that I will try to use that as a motivating path throughout these lectures. Okay, so let's say we have some two bodies, this one and this one. We're going to send them in towards each other with some energy. I'm going to call the energy square root of S divided by 2. Okay, so from that you can already see that I'm taking a particle physicist approach and already using the appropriate notation. So this is the energy. And I should say in the lectures I'll be using mostly units in which C and H bar are equal to 1, although at some point we'll try to restore H bar in the future lectures to try to understand which aspects of this story are classical and which ones are quantum. Okay, so what we can do is build up some wave packet or maybe some soliton or something like that. Okay, which is basically some density of a scalar field. Then what we do is we minimally couple it to gravity. Okay, and then we send them in, these two bodies, at some impact parameter. Let me call the impact parameter B. And then we're going to start asking what happens, right? So the basic aspect of it is given by the so-called Hooke conjecture. Okay, the Hooke conjecture dates back to the work of Kip Thorne in the 1970s, 72. oh, I should say, before kind of moving on, every time I give lectures on these kind of topics, there's always a lot of people asking me afterwards for references and so on. So what I decided to do this week is to preemptively upload a lot of references that you might have seen on the Google Drive. So for example, this one you can find under the lecture number 1. There's also a number of global references, which are more like reviews of the whole topic that I find particularly useful. And I should also say that I've kind of tried to select the kind of most readable references, not any crap, just like the ones that I think are the most intuitive to understand. Okay, so the Hooke conjecture says the following: if I have some body, which could be some bunch of mass and energy, and then let's say I manage to put a hoop around it with the radius r, diameter 2r, then the conjecture is that that body collapses into a black hole. Provided that the radius of the hoop is smaller than the Schwarzschild radius of the corresponding body. So Rs is going to be the Schwarzschild radius. Okay, so in our case, Rs is going to be, well, everything is dominated by the energy. So I can say that roughly this is supposed to be 2gm. So I can just call it asymptotically, just if we're interested in things up to order 1 numbers, is g times the square root of s, where square root of s is the energy of this body. Okay, so let's apply this Hooke conjecture to this setup. And actually, first, let me discuss the kind of simplified version of the head-on collision. So the head-on collision means that the impact parameter is exactly 0. So they're just like we're smashing the two solitons together, just like at a particle collider. Okay, so this was actually first analyzed by Roger Penrose back in the 70s. And although I believe the manuscript in which this was analyzed was unpublished and then rediscovered later on. But what I wanted to really mention is that, so this was an analytic work, of course. But on top of that, more recently, there's been a lot of work on these kind of problems using numerical GR. And what I like about numerical GR is that you can just look at the pictures of these things scattering, and you can see with your own eyes what's actually happening. So the pioneering paper on that topic has been done due to Chaptuk and Pretorius in 2009. So I actually really recommend reading this reference because they have a wonderful discussion of the whole setup. Okay, and one thing that we can ask, well, now we've set the impact parameter to be 0. So the only parameter only kind of important parameter that we have that we can play around with is the s. Okay, so the question is what happens as we keep increasing the energy? And according to the Hooke conjecture, well, at some point this threshold radius is going to grow. So at some point it's going to go above the radius of the body that you create. So that happens roughly at up to order 1 numbers, r over g squared. Right? And then to the right of it, we're going to have a collapse regime. So this is the regime in which the outcome of this numerical simulation is going to be that we're going to end up with a black hole. Well, a black hole, and there's going to be some radiation flying out. Actually, one of the interesting aspects that was known only due to the numerical GR computations is that the roughly order 0.1 fraction of the energy gets lost to gravitational radiation. Okay, which at least to me was surprising that such a large fraction, which depending on the specific setup could have been like 20, 30, 40%, actually gets emitted away. Okay, so this is above the transition, which is roughly here. And maybe I can straight away invite some audience participation. What do you think happens below the transition? So we smash the particles, but not at super high energy. Okay, people are like bouncing back. What actually? No, that's more or less correct. What actually happens, and you can look at the pictures in this paper. They actually pass through each other, and they kind of disperse in many directions, although preferentially along the axis of the scattering. Okay, so let me just kind of cartoon is that they do something like this. So let me call this. Let me call this this regime dispersion. Question.
What are the assumptions we're making about this cluster of matter? Is this number R like well defined throughout the collision? Will it distort? Will it?
Yeah. So for now. Oh, sorry. So the question. I was supposed to repeat the question. The question was, what is exactly the meaning of this R? What's happening in the middle, and so on. For now, I'm kind of wanted to be intentionally vague. Basically, we're just trying to get some intuition of like there's supposed to be two regimes. How exactly we talk about this transition is going to be something that we're going to be more precise once we set it up analytically.
And this Hooke conjecture is a classical statement, or do we assume quantum correction?
The question is about the Hooke conjecture, whether it's a classical or a quantum statement. This is purely classical. Any other questions? Yeah. The square root of S is the energy of the. So I'm using the particle physicist. I'm going to be more precise about that. I'm using particle physics terminology in which S is the center of mass energy squared. All right. So yeah.
So I guess the assumption here is that we're scattering from something that's asymptotically Minkowski.
Yeah, the question was whether we are doing it in asymptotically Minkowski space, and the answer is yes. Okay, so this was more or less a warm-up to a more complicated setup. So here we've studied what happens as a function of S, but we've kept B to be 0. Now you can already anticipate what's going to happen next. We're going to basically study what happens as the, excuse me? Yeah, thank you. What we're going to do is add another axis. And this is what is going to result in the so-called phase diagram of gravitational scattering. And maybe I should say straight away that everything that we'll be talking about, at least today, is classical. And then we'll discuss quantum corrections in the next lectures. Yep.
One more question. Now, when you said B is equal to 0, you just mean that B is much smaller than R?
Yeah. So R, roughly speaking, you can think of as the kind of extent of this soliton, and then really what I meant is that B is much smaller than R in this case. Okay, excellent. So now what we can do is we can add this other axis. Okay, so we're gonna have S, and then on the other axis we're gonna have B. Of course, on top of that, we can add all sorts of other effects. So you can think of this as being some very high-dimensional space in which we add various different effects like spin, the space-time dimension, the kind of internal structure of these bodies. But what I'm going to do for the purpose of this lecture is I'm going to ignore most of that, and I'm going to focus specifically what happens as a function of S and B, which is a difficult enough problem in its own. Okay, so we know that somewhere here, there's going to be a transition between the collapse and the dispersive regime. So I can anticipate that something like that is going to happen, that the collapse regime is going to be still valid at high energy, but if the impact parameter is small, at least small enough compared to the extent of the objects. Okay, so that's one kind of extreme. Another extreme that I can study is roughly here. Okay, so this is the regime in which the energy could be large, but B is much, much larger. So this is the regime in which I have two bodies that are very far away, and they interact gravitationally. And as you might expect, this is a regime in which everything is dominated by just like tree-level computations. So we typically call it the Born regime, or you can think of it as a kind of Minkowski regime. And one thing that distinguishes this regime from this one, even though both are technically speaking high energy, is that the collapse regime is going to be the domain of strong gravity, even though classical, and the Born regime is going to be the domain of weak gravity. Okay, so these are the two extremes. And now we can think of what happens when we tune from this regime to this one. So one way to think about it is that we can, for example, fix the energy, and then we can study what happens as you start scattering at smaller and smaller impact parameters. Or the other way is that you fix the impact parameter, but you increase the energy. Okay, so the question is, what happens here? So maybe we can have some guesses or educated guesses from the audience. Bound states, yeah? Excuse me? There's already professional terms dropping from the audience. So yes, let me include that, iconal. So I'm actually going to explain what iconal is in the next lecture. There was the bound states. Anything else? Scattering. In a sense, all of it is scattering, I guess. But yeah, let me just include that. All right, give me more. Dispersion, yeah, that's a good one. So dispersion in the sense, the dispersion here means the production of gravitational waves. So let me just call it gravitational waves in here. Okay. Any other ideas? Yes?
Is there enough matter details to cause like fusion?
Yeah, that's a good. So the suggestion is whether there's going to be some fusion or something like that, depending on the details of the bodies. Let me kind of let me avoid the topic of fusion directly, but kind of there's going to be effect, which is the effect of the finite size of these bodies. Very often we call it the tidal effects, and the reason is that if we think of these two bodies as approaching each other and starting to spiral, at some point there's going to be a drag effect in which the bodies get stretched. Okay, so this is known as under the umbrella of tidal effects. So basically, what's going to happen is as we go from this regime to this one, all of these things will have to switch on at some point. So what I decided to do in this set of lectures is basically keep exploring this diagram. I believe actually you've seen this diagram in the first lecture of Sasha Zhibovedov, and tell you about how these different effects switch on and how to understand this scattering from the perspective of the S matrix. So how to use particle physics tools to understand that. Okay, so the rough roadmap is that today, in the first lecture, we're going to focus just on the setup of the problem, how to even formulate this problem in the language of scattering theory. Then in the second lecture, we're going to include corrections to this which is known as the iconal approximation, which is the relativistic analog of the WKB approximation. This is going to give us the language in which we can think of the corrections to this picture. And then we're going to talk about these kind of gravitational wave, tidal effects, things in the third lecture. This is optimistically assuming I can go through my notes. And then in the last lecture, we're going to go beyond these kind of particle physics approaches, and I'm going to tell you a little bit about what happens if you include stringy corrections. Okay, so in the stringy corrections, we think we have some handle on how we can cross this boundary between the collapse regime and the weakly coupled regime. Okay, any questions about the motivation?
The stringy regime we expect to pick up at low energies in this stuff?
Yeah, so indeed, there's going to be some. So it's easier to think of it from the impact parameter perspective. If we tune the impact parameter to be low enough, below or comparable at least to the string scale, then we can include those corrections, and those corrections would be valid somewhere here in this strip. Okay.
This diagram was supposed to be classical. So somehow you're saying that.
Yes, excellent. Yes, so sorry, I was supposed to repeat the questions. So the question was about the classical nature of this diagram. So indeed, this regime of the high energy, so by high energy here, I mean the impact parameter being large and the S being large simultaneously. But as you can see from this diagram already, the kind of rate at which one becomes large compared to the other is going to be governed by different regimes. So all of that I would call classical. And as we go closer and closer here, there's going to be some barrier in which we start including quantum effects. So I'm going to mention that a little bit as well. Yes?
I think stringy regimes can also exist at large E because when for highly exact string is also very long.
Yeah.
So it can also exist at large.
Exactly. So the question was about string corrections in the kind of large B regime. Indeed, we'll do a computation and we'll see that stringy corrections here, but they will be exponentially suppressed with B. So they exist, but they're becoming smaller and smaller. Right, excellent. So let me move on to the setup. So before doing that, I wanted to review a couple of things. Whoa. About the S-matrix approach. I just wanted to include this little blackboard here to emphasize one point, which I think is very often confusing when people talk about the S-matrix. Okay, so let me remind you, the S-matrix is the overlap between the wave function of the in states and the out states. Or you can think of it as preparing some wave packets, evolving them with the S operator, the scattering operator, and then reading off what happens on the out state. So let me distinguish actually between two notions. One is something I will call the physical S-matrix. Physical S-matrix, by definition, happens in nature. So for example, or in a numerical simulation, when you're doing this kind of simulation, you have all sorts of effects that have to do with the finite nature of the particle, also finite nature of the scattering box that you put it in. So there will be an object that, technically speaking, should be called the physical S-matrix, and it's going to send in to out states, but it's also going to depend on all the details of the way that you prepare those states. And one thing that is going to be important for this lecture is that, in principle, it can be also dependent on the time scale of your experiment. Okay, so it's one of the basic facts of the S-matrix that the S-matrix could, in principle, depend on the size of the experiment. Let me contrast that with I'm going to call it, for the purpose of this lecture, the idealized S-matrix. Idealized S-matrix is what we learn in QFT courses, Peskin-Schroeder, Srednicki, Schwartz, and so on. This is the one in which we made a lot of idealized approximations. And the reason for that is that it's easier to compute it this way. So the main idealized approximation is that we model wave packets by point particles instead. Another one, which is going to be crucial today, is that we also take the limit of the separation between states going to infinity. So we take this limit, we pretend that the states on the in and out are asymptotic states. And crucially, this assumption here can actually break down. Okay, so it breaks down, and it's actually related to the topic of infrared divergences, or IR divergences. But one thing that I wanted to emphasize is that every time you see an IR divergence, it's actually a physical effect that has to do with the size of the experiment that we're measuring here. It's just easy to forget because in the setup, it looks like something wrong gets done. Okay, so we'll encounter some IR divergent objects in this lecture. Okay, so with that preface, I wanted to focus on the kind of first question of we wanted to define some observables that have to do with this scattering process. So the natural question is, what can we actually measure? Okay, so the objects that we can measure from the asymptotic infinity, or at least large distances, is something that I like to refer to as the asymptotic observables. And one reason why I wanted to mention them is that to also make a little connection to the lecture of from this morning. Okay, so one thing that we can try to measure, kind of inspired by the S-matrix approaches, is the total cross-section. So let me explain a little bit what that is, just to introduce the notation. So total cross-section, let's say we have particles 1, 2, and they can go to anything else in the spectrum of your theory. Okay, so this is going to be proportional to, and now I realized I forgot to mention that the S operator, hopefully all of you have seen this at some point, traditionally is decomposed into the identity plus the interacting part with the I, which is a convention. Okay, so when we talk about the cross-section, what we do is we do with this symbol I mean, we're going to do a sum over all on-shell intermediate states and an integral over their phase space of the T matrix element of 1, 2 going to anything, and then its complex conjugate. Okay, so in the language of the blobs, how this looks like is that there's two particles, two coming in, they interact with the T matrix element, and then on the other side, the same particles emerge, but they're evolving with the T star or T dagger operator, which essentially means that the time is reversed between the two. And then in the middle, we have to sum over all sorts of stuff that happens. Okay, so by inserting a resolution of identity in here, we see that we have to sum over all intermediate states, which could be the black holes, the two heavy bodies themselves, but also some radiation and other effects. Okay, so that's the basic observable. Is there a question?
The right-hand side X seems to be a dummy variable, but there's an X on the left-hand side. What's that?
The question is about this notation. This is just notation. Usually people would call it 1 to total or something like that. It's just a notation. The reason why I included this notation is that we can also talk about generalized cross sections. These ones are actually the ones that are the most useful in the modern literature. So let me call them semi-inclusive cross sections. Okay, so here, let me just skip the formula. Let me give you the picture. This is the one in which you start with particles 1 and 2, and then you evolve them to anything, but you also put an operator that you measure as the intermediate state here. Okay, so in this blob picture, the picture would be something like this, and it's almost identical, so you can sum over stuff in the middle. But on top of that, you also bring an operator that you measure in here. So one example of such a measurement, so typically it would be this plus its complex conjugate. One example of such a measurement would be if you have two bodies that are scattering, and then you're trying to quantify the amount of radiation being emitted in this process. So you measure that radiation in the future. So the way that you should read this diagram is that the time is evolving from left to right because we evolve with the t operator. But when we have t dagger or t star, the time evolution gets reversed. So time actually goes in this direction. Okay, so this is obvious from the cross-section point of view. We just scatter everything, and then we sum over whatever happens on the outgoing state. This is what we do here, except we also measure inclusively this third operator, which could be something like the value of the metric, or even better, a curvature, or things like that allow us to quantify the amount of radiation at infinity. Okay, so one example of that, which is particularly famous nowadays, is called the waveform. The waveform because it's the profile of the gravitational waves emitted in such processes.
Very quick question.
Yeah.
I'm confused about the picture. If I'm measuring something in a collider, I'm measuring the outstates. How would I distinguish between the three and the stuff on the right-hand side?
The question is how you would distinguish between free going this way and free going this way?
Like just the external part. Like all I measure is I know what the external particles
Yes,
are.
yes.
This all seems like.
That's actually one, yeah, exactly. So this is actually one of the points, is that it is not enough to specify which particles are incoming, which particles are outgoing. What you also have to specify is how they evolve with the time operator. This is actually closely related to what Tom Hartman mentioned with the Schwinger-Keldysh formalism, that you're really thinking of this as having two states, and then they evolve, you insert the third operator, and you evolve back. So actually that information is supposed to be there, and this actually gives you after summing with the complex conjugate, gives you the expectation value of an operator in the background of the states that you've prepared. There's a question. Yes, this is an example of what I would call an asymptotic observable. So just let me clarify. Free, even though I've put it in the middle, is actually in the far future. So with this, it's related to the 5-point scattering, but not quite. If you actually compute these objects, they differ from 5-point amplitudes. Okay, so these kind of generalized amplitudes which depend on the time ordering is something that I would call asymptotic observables. Okay, and since we mentioned the scattering amplitudes, let me mention that as the last example. So these are to distinguish them from inclusive quantities. Let me call it the inclusive amplitude. And this is the type of the object that all of you would have computed in your QFT courses. So in pictures, this is just evolving with the t operator and having some stuff like this. Oops. Okay, so you can talk about 2-to-2 scattering, 2-to-3, and so on, so on. So it turns out that in the order of complexity of how difficult it is to compute those objects, this one is the most difficult, this one is easier, and this one is the easiest. So if I had a continuous blackboard, I would have kind of say that it gets easier as you go down in here. So for this reason, the focus in our lectures is going to be this object, mostly, although we'll see that in you know, if you wanted to compute this object, it's clear that it provides building blocks for the other ones. So I'll actually mention that as well. There's a question, yeah.
The first two by acting this LSC are like out of time order correlators.
Yeah, the question is if I get these two observables from the if I can get it from an LSZ reduction, and the answer is yes. So there's a modified LSZ prescription, which you start with something like an operator of this type. Say. Okay, time ordered, anti-time ordered. You LSZ that, and then this gives you the cross section. Yeah. This is actually supposed to be the little connection to the previous lecture from this morning. And another thing that you can read about if you're interested, the reference is on the Google Drive, is that these observables are also connected by analytic continuation. In the morning, you heard about analytic continuation in position space. There's also an analogous analytic continuation in momentum space, which is related to crossing. Okay, so as I mentioned, what we're going to do mostly in these lectures is we're going to focus on the exclusive amplitudes. So the simplest of the exclusive amplitudes is going to be the 2 to 2 amplitude. So let me just include some notation. Okay, so I'm going to have particles 1, 2, 1 prime, 2 prime. The overall energy I'm going to call S. So these are called Mandelstam invariants. I believe everyone is familiar with those. Okay, so the first one is going to be S, which is in my conventions P1 plus P2 all squared, so the center of mass energy squared. And the second one is going to be T, which is the invariant in this direction. T very often is also represented as minus Q squared. So you can think of Q as the momentum transfer in this direction. So it's the space-like momentum that is being transferred between this particle and this particle as they scatter. Okay, so that's called T. Okay, so in the physical scattering, S is positive and T is negative. That's why we often write it as minus Q squared. Okay, so maybe let me just write it. This is the center of mass energy squared, and this one is the momentum transfer. Squared. And then finally, another common variable to describe this process is the scattering angle. So the scattering angle is the angle that say in this notation, particle 2 is deflected by. And you can actually do a little exercise. The exercise is some geometry problem to translate how this theta can be written in terms of S and T. There's only two independent invariants. So that's how we know that it can be expressed in terms of the other ones. And the formula is 1 plus 2t divided by S minus 4m squared. I believe you've seen this formula many times 2 weeks ago. Well, actually, one of the simplifications that I'm going to do in most of the what I'm explaining, so m is the mass of the external particles, 1 and 2. In most of the lectures, I will set, for the derivation that I'm doing on the blackboard, I will set mass to 0 for simplicity, and then I will often quote the answer of what would happen if you included non-zero masses. Excuse me?
So the concept of mass makes sense in particle physics, but in gravitational interaction, what do we mean by external mass? How do we separate what is the mass from the square root of S?
Oh yeah, so the question is how do we interpret the mass in the massless theory? So basically the positive mass would correspond to just the mass of the blobs that we scatter. The zero mass would correspond to, instead of having blobs of matter that we scatter, instead having shock waves. So like plane waves that come from infinity and they scatter for each other. Okay, so that's there's some little discussion also whether the limit is continuous or not, but I'm going to skip that, I guess. Okay, so next up, let's start computing, basically. I mentioned on the phase diagram, let me pull it up. On the phase diagram, we had this simple Born regime that was supposed to be governed by tree-level exchange. So let's actually let's get some formulas for this. And I think these formulas might look familiar from the lectures by Simon Caron-Watt 2 weeks ago. So I'm going to very quickly remind you about the tree-level or Born approximation. Okay, so if you just compute it from Feynman rules, we have this object, let me call it T3. We know already it's going to depend on S and T, the Mandelstam invariance. And you might know that it's going to be given by the tree-level computation is just summing over 4 diagrams. Okay, called the S, T, U, and the contact term. And you probably all know very well that in the limit, I should have mentioned one thing, that this Q that we had here, the impact parameter, is something that is canonically dual by a Fourier transform to the, Q was the momentum transfer, is canonically dual to the impact parameter. So maybe let me write it here. You should think of Q roughly as 1 over B, at least approximately. So if you wanted to study this regime of the Born approximation, in which B is very large, this is the limit in which Q is very small. Okay, so in the limit as Q is very small, these 3 diagrams are going to be subdominant. And what's going to happen is that this diagram, because it has a 1 over T pole, is going to be enhanced. So this is dominant in the limit as T is very small compared to the S. So the minus sign is because T is negative. Okay. So that means that in this limit, the computation actually simplifies quite vastly. It simplifies for 2 reasons. The first reason is that we're only having 1 diagram out of 4. But there's actually another reason. Can someone remind me what the reason is? I'm just testing how much you remember from 2 weeks ago. Anna?
The propagator just has 1 term.
Yes, the propagator is 1 term. So what the significance of the T goes to 0 is that the intermediate propagator is the T channel propagator. So T going to 0 is the same as the intermediate particle going on shell. So intermediate particle going on shell means that effectively, the only thing that you're doing is you're gluing together 2 on-shell amplitudes. Okay, so all of this computation is actually just dominated by this. Let me remind you that the little notation with the dashed line means that the particle crossing the dashed line is on shell. So in this language, T goes to 0, this graviton becomes on shell. It's a soft graviton. So the only thing that we have to do is glue this amplitude and this amplitude. Okay, And through the magic of the S matrix, you might know that these amplitudes are actually entirely fixed by symmetries. So these are on-shell amplitudes. They're free particle amplitudes. They're entirely fixed by Poincare invariance. Poincare covariance, strictly speaking. Okay, so I could do the little computation here, but I think you've seen this computation, how to do the amplitudes and so on. So let me skip that detail behind and just give you the answer. The answer is going to be this plus subleading terms. Okay, so as promised, there's 1 over t. This is the t-channel pole. There's the g, which is the interaction. This is the g Newton. And there's 2 powers of s. So these 2 powers of s are related to the fact that we have graviton exchange. And graviton has spin 2. This is a spin. So for example, if we scatter the gluon, 1, and so on, and so on. Okay. Okay, so now let me leave a couple of exercises just to reiterate that this is nothing new. You've all seen this before, be it 2 weeks ago or back when you studied your QFT. Is that one thing that you can do with this amplitude? Well, first of all, let me quote the massive case. So a little exercise, repeat the whole calculation, but in the massive case. And the only difference is in the massive case, the numerator s squared gets upgraded to some more complicated function of s, and that function is just s minus m1 squared minus m2 squared minus 4 this. Okay, so if the masses go to 0, it just goes back to s squared. Okay, and once we have this result, the actual exercise is to derive the Newton's potential which in d dimensions, it would be, of course, proportional to this. Okay, so this all is supposed to follow just from the graviton exchange. All right, so this you can do in your own time, which I heard you have plenty of your own time. So, sorry, there's a question.
Sorry, I'm suddenly confused. So when
Yep.
I think you're talking about some localized object.
Yep.
And for localized object, how can you define the momentum? I think from uncertainty principle.
The question is, how do we define momentum for the particles?
Yeah, for the localized object.
It's the usual thing. I'm just scattering point particles, which in QFT are plane waves. This is just usual QFT. So I'm assuming that each particle has a well-defined momentum.
Yeah, but then for plane wave, how can we talk about the compact factor?
Yeah. Yeah, so you should, at the beginning of all the QFT books, you learn about the Gaussian wave packets, and this is how we're actually supposed to think about it. But then people argue that, we can actually simplify our life, a little, hand waving, and then we actually think of it as the plane waves. Yeah. Okay, so in the final part, what I wanted to focus on is the fact that so far we've done everything in momentum space, but this diagram in here is produced as a function of s and b. So it's kind of half in the momentum space in terms of the energy, but b is a spatial variable. So what I need to do is tell you how to translate between b and the t variables. Okay, so this is known as the impact parameter transform. And actually, I can use this opportunity to summarize a little bit the different objects that you might have seen throughout the last couple of weeks. Okay, so the object that we've been computing over there is the matrix, exclusive matrix element as a function of S and T. Another object that I believe you've studied thoroughly in the lectures by Sasha Zheboedov is the S matrix as a function of S, but the other variable is the angular momentum, J, or the partial wave spin, J. And then what I'm going to talk about, which I believe you've also seen, is yet another object which takes the variables that it uses is S and B. And this is precisely the one that we wanted to study here. So maybe before kind of telling you how they're related, let me tell you a little bit about why do we have three different things? Why do we study things in different variables? It seems a bit redundant. But as usual, some variables are better for some problems, and some variables are better for other problems. So for example, as exemplified using Feynman diagrams, the S and T variables are very friendly towards perturbation theory. Okay, maybe someone can tell me what is so useful about the partial wave amplitudes? Reggie limit is one. Unitarity is probably the most important one. Let me include unitarity and Reggie as well. So remember that we're going to come back to that in a second. While the unitarity in the partial wave, in the plane wave basis is given by a convolution of the intermediate states. In the partial wave basis, it's just multiplication. So that's what's so easy about it. In a sense, that basis diagonalizes unitarity, elastic unitarity. Okay, and then finally, what's so cool about S and B? Anyone? Exponentiation, and this is exactly what we expect in the classical limit. Okay, so since I wanted to tell you about these kind of universal classical aspects of the gravitational race matrix, it is natural to go to this basis. Okay, and let me finally tell you that all of these are related to each other. So if you compute things in one, you can translate it to another basis. Okay, so here between this and this step, we have the partial wave expansion. What we have here is the so-called impact parameter transform. And I'm going to write it in a second. And likewise, you can also, it's a commutative diagram, so you can always apply these two in sequence, or essentially what this gives you is some kind of a Bessel transform. Okay, so the strategy would be that, for example, if you're doing a perturbative computation, you would do it here, and then translate it to this one and see some aspects of exponentiation and things like that. Okay. Okay, so let's actually do it. We've already computed an object here at tree level. So let me give you a tree level approximation to this object as well. Okay, so first of all, I need to tell you a little bit about this transform. Okay, so this transform is going to be defined as follows. So I have in my S, and I'm going to claim it can be written as follows. Let me write it down first. As I mentioned already, the Q and B, the impact parameter, and the momentum transfer are related by a Fourier transform. And the thing that we stick inside of the Fourier transform is the plane wave amplitude, the one that we've computed at tree level. This factor of 1 here is precisely the disconnected term. So remember, in the language of the operators at the beginning, I told you that S is decomposed as identity plus IT. So this identity essentially becomes the 1. And the interacting part is the rest.
There minus q squared as before.
Oh, yes, minus q squared. There was a typo here. Thank you. So, and all these like weird factors of 1 over 2s, 2 pi to the d over 2, it's some normalization. One way to fix this normalization would be to actually include the disconnected piece here, do a transform, and see that it gives you 1. So this is how you can convince yourself that these factors are supposed to be here. Okay, and maybe one other thing that might be confusing is this d minus 2. Okay, so the way that you should think about the scattering is that there's some particle 1 and there's some particle 2 that are scattering at very high energy, so they're highly boosted. And the way we can think about it is that one of them travels along the one side of the light cone, like the u coordinate, and the other one along the v coordinate. But what they have to do is they have to exchange gravitons. And these gravitons are essentially exchanged in the direction perpendicular to the blackboard, which is d minus 2 dimensional because we've already used the u and v. Okay, so that's the physics behind this transform. And one thing that we can do now is we can plug in the tree level approximation in here. So let's do that. Okay, so S3 is going to be given by basically plugging in this minus I 8 pi g s squared over t into this formula. Oh, yes?
Small confusion is b vector here and b like a scalar there.
Yes, thank you so much. So it turns out the question was about why do I write b? So by b, I will always mean the absolute value of the impact parameter. It might be a little bit confusing that here it appears as a vector, but here it appears as a scalar, just the value, just the norm of this vector. But this was in fact guaranteed by counting the number of degrees of freedom. I started with 2 degrees of freedom, S and T, and I have to end up with 2. So it turns out that actually after you do all of this, only the absolute value of b matters. Yes?
So here you're not only plugging in the tree level approximation,
Yeah.
but also the one where you only kept the diagram with the T exchange.
This is the tree level. Yeah.
But
Oh, yeah, sorry.
you said you had this 1 over T pole,
Yeah.
but here you're doing an integral over all values of T, it seems.
Yes.
So is it valid to keep only the diagram with it?
Oh, yes, that's an excellent point. So let me actually write down the formula, then I'm going to explain so here I'm just going to plug in just copy the formula. Okay, so it looks something like this. There's a minus sign that cancels the minus sign from the q squared. And the question, it was an excellent question, was about why I've dropped the subleading pieces in Q. Why am I allowed to integrate over the all of Q? And if you actually do this exercise, you would find that the terms that I've dropped are either constant or polynomial. And the constant or polynomial gives me a delta function or derivatives of the delta function. So actually the things that I'm dropping are entirely local. Like they don't affect the long range, long B physics. Excuse me?
They also cancel the 1.
So in the, I guess, tree level, I mean things proportional to G. So I excluded the 1 from the computation. Yeah. Including the 1 is going to be very important tomorrow. We're just not, oh, I erased the diagram. We're just not interested in them because there would be low B. There would be contact terms in B. Yeah. Okay. There's actually a whole strategy called the method of regions, which allows you to study when are we allowed to drop some contributions, which eventually are going to integrate to things that we don't care about after Fourier transform. Okay, so let me actually do a couple of steps in this integration. Okay, so the first step would be to basically change the coordinates. Okay, so I have some B and I have some Q. There's some angle between them, say phi. So it's maybe already obvious that most of these d minus 2 directions, they're very simple to integrate out. The only thing that matters is the absolute value of Q and the angle between B and Q, which is the phi. Okay, so if I just give you a couple of steps, what's going to happen is that I can essentially change my integration boundaries, and there's a reason why I wanted to go through these steps, from to have the norm and the angle, and then upstairs we're going to have the absolute value of Q, absolute value of B, and cos between these two, and the Q squared, as well as some Jacobians. Jacobians you can just fix by the mass dimension. It's clear that there's to be Q to the power of D minus 3, which is the number of integrations I lost. And there's going to be some like volume of D minus 2-dimensional space. Let me just call it a hashtag for now. Okay, and the next thing that I can do, now the integral of the phi is becoming very simple. So those of you did I miss a sign? Yeah, I guess it should be cos of theta. Maybe let me write it like this. Oh no, it does not. It does not depend on the dimension. The only dimension dependence comes from this, which you could have guessed by the mass dimension. Oh yeah, that's included here. So that factor also depends on the dimension. Excuse me? I don't think so. The only thing that I've done is converted b dot q into b dot q times the cos. Yeah. So those of you who would have suffered through your math methods courses in undergrad would know that what this integral integrates to. Actually, I think it was correct. Sorry. I'm getting too easily influenced here. There's going to be this integral here is an example of a Bessel function, okay, J0, which is going to have this argument here. And let me copy the q to the power of d minus 5. And the only thing that you need to know about the Bessel function is that it starts at 1. So this Bessel function here, if I plot it as the function of the argument, it starts at 1, and then it oscillates a little bit, and then it decays. Okay? So the reason why I wanted to go through these steps is to emphasize when is this integral dangerous. Well, one place where it's dangerous is if d is equal to 4, because this becomes 1 over q, and I integrate over dq. So you see that there's a divergence. The divergence is suppressed at large q because of the Bessel function, but it's not suppressed at 0. Okay, so actually the bottom limit here gives me an IR divergence when d is equal to 4. It's actually divergent also when d is less than 4, but I'm not interested in lower dimensions. Okay, so at this stage you can actually do this integral. Let me give you the answer. Okay. The only trick was to recognize the divergence. Okay, and then the answer is going to be, let me just copy this. Now I can restore all the factors of d by copying them from my notes. Okay, you see that there's nothing interesting here. The only interesting thing is that when d goes to 4, we have gamma of 0, which is a divergence. So this is how we see the IR divergence. So if d is equal to 4, you actually need to regulate this integral. And then if you do so, you get this factor here, where this delta t is the IR regulator, which was the size of the experiment. Okay, so let me maybe emphasize this. Okay. So we're actually going to come back to this log, and then we're going to see that it has physical consequences, and some of those physical consequences have been even measured in experiments. But for now, what I wanted to look at is the S dependence of, the S dependence is the same. It essentially followed from the fact that the tree level amplitude here was looking like S squared, and there was 1 over S normalization. Okay, so maybe someone can tell me what is so wrong about this S dependence. Sorry, yes? Yes, okay, jackpot. Okay, good. I thought it's gonna take a couple of tries. But the answer is that the S matrix grows without bounds. And that actually turns out to violate unitarity. So let me continue here. So this is the last topic for which I have seven minutes, I guess. 6, okay. What can I do? Okay, so the last topic is the violation of unitarity. Okay, so here let me just make a connection. Remember that it was the easiest, I claimed at least, it was the easiest to study unitarity in the partial wave basis. But hopefully for us, at large impact parameters, what happens is that we had these two particles that had the energy squared of S over 2, and they were separated by the impact parameter B. So I can, even classically, I can estimate what is the angular momentum of this two-body system that is getting created, right? They're separated by B, there's some energy here, right? So I can do my undergrad computation, and the angular momentum is just the J is roughly speaking square root of S over 2 times B. Okay? And the twiddle is because this result is valid in the classical limit. Okay? And now I can come back to so what this essentially means is that when I study the mod square of my amplitude, S, that, roughly speaking, is going to be the mod square of the partial wave amplitude that depends on J and S, where J is identified with this. And this one you've seen not so long ago that it's actually bounded by 1. So this is the unitarity bound. Which, technically speaking, elastic unitarity bound. The reason why it's an inequality is that there could be inelastic contributions, so like gravitational wave production. And then what we see is that, let me wrap it up here. What we see is that this bound is clearly not respected at high enough energy when this quantity, G times S, becomes large. Okay, so this is violated at high energy. So roughly because S3 grows as GS, say in D dimensions, B to the D minus 4. Okay. Clearly for large energies, this cannot be satisfied. And what does it mean? Every time you see something like this in particle physics, it's a sign of the fact you have not included some contributions that are supposed to rescue this unitarity bound. Okay? And this is known under the name of unitarization. Okay, and what it means is that if we come back to our phase diagram with S and a B, what I mentioned is that this Born regime is valid somewhere here. And now what we've done is we started from there, and we kind of went out of the region of validity of this approximation. The way that we know we went out of this region of validity itself is precisely this computation. So it turns us when the energy crosses this threshold, then we have to expect new physics. Okay, so what this means is that here, new effects must save unitarity. So let me leave you with a small conundrum that you can think about in your vast free time between this lecture and the next, which is we've already seen that we've included all the classical contributions, the tree-level contributions. Okay, right? Every QFT book tells us that the classical contributions are the ones given by tree level. So naively, we've already included all the classical physics, at least the kind of Minkowski approximation of physics. But we know that even classically, the thing that has to rescue us is the GR corrections to Minkowski physics. And the conundrum is, where do they come from? Okay, it seems like we've already exhausted all the diagrams available to us. So the question is, where is GR hiding in these perturbative computations? So we're going to resolve that conundrum tomorrow at 2 p.m. Thank you.